이제 잠시 후
Ladies and gentlemen, IAU General Assembly 2022 public lecture will start shortly. Please, ladies and gentlemen, please take your seats, and also please silence all of your electronic devices, including your smartphones. And we're providing you with simultaneous interpretation services. So we have Professor Lim, Professor Song, who will be translating today's lecture. And please turn to channel 1 for Korean, channel 2 for English. And we are also joined by online participants. And if you log into Chaos Foundation channel, you will be able to hear both Korean and English. And in the YouTube IAU channel, you will be able to listen to the English presentation, and you will also see the subtitles. There has been some time lag between the actual sound and the subtitles because of the technical difficulties, and Professor Lee will be answering some of the questions that you will be posting on the chatting room. So we will see you at 7 o'clock on the dot.
네, 안녕하세요. 지금
Good evening, ladies and gentlemen. We'll now begin public lectures for IAU General Assembly, and I'll be your MC today. My name is Kim Jung-mi. I'm from Ewha Women's University. Today was especially hot and humid, and we are joined by many people who have taken time out of their summer night to be here with us. I would like to especially welcome young students, and I would like to once again ask you to silence all of your mobile phones. And we are providing you with simultaneous interpretation services today. I believe you have received one of those receivers for translation services, channel 1 for Korean, channel 2 for English. And on your way out, please make sure you return your receivers. And a lot of people are watching this lecture through YouTube, and both of the channels will show the English presentation with Korean subtitles. I hope you can join us until the very end of this public lecture. Well, some of you might wonder how we came to organize this week's public lecture. In Bexco in Busan, as part of International Astronomical Union General Assembly, 31st General Assembly is taking place in Bexco this week, and we have astronomers from all over the world joining us for this General Assembly, and the theme of this year's General Assembly is Astronomy for All. And we are trying to accommodate as many people as possible in this world of astronomy, and we have invited globally renowned scholars to deliver this public lecture. And I believe you have paid for registration for this General Assembly, and full amount of your registration fee will be donated to IAU, and it will be used for advancement of astronomy in developing countries. Thank you very much for your financial support. We heard from Professor Shepard Dolman yesterday about black holes. Now we are joined by Professor Brian Schmidt. He will talk about the acceleration and expansion of the universe. So we have audience online and offline joining us today. So let me briefly introduce you to Professor Brian Schmidt. He's an astronomer. As you're well aware, he is also Vice Chancellor and President of Australian National University, and he is famous for his research in accelerated expansion of the universe. He has received numerous awards, and in 2011, he received the Nobel Prize for Physics. He's an active researcher, and he's also a great communicator for science. He is also active in educating and training next generation scientists. And he is also leading a research in Southern Sky Survey team using SkyMapper optical telescope located in northern New South Wales of Australia. So we would like to invite the title of today's presentation is The State of the Universe, and that is translation, that is how the universe looks like at this point in time. When the lecture is over, we are going to open the floor to the audience for questions. So now we would like to welcome Professor Brian Schmidt with a big round of applause.
To Professor Brian Schmidt.
Sorry about that. Welcome, everyone. And it is great to be here in Busan, here to talk as part of the IAU 2022 meeting about the state of the universe. Now, here today in this audience and here in Busan over this 10-day period, we have astronomers from around the world who are going every day about, as part of their lives, making cutting-edge, breaking discoveries that I'm going to try to tell you the story of today. Now, there are so many things going. I actually can't tell you everything that's going on. And to my friends in the audience who are these astronomers, I will try to acknowledge at least some of the work done, but I cannot possibly cover it all. Astronomy is such a rich field right now. We live in a time where we are literally discovering each year tremendous amounts of things we just simply didn't know 10 years ago. So today I want to talk around the universe as a whole. So let's start at the beginning. Long ago, long before stars and galaxies, something happened. The universe as we know it was created, expanding in all directions. It was very hot and dense, and it cooled as it expanded. And we call this time the Big Bang. Now, what was the Big Bang? I don't know. No one actually knows what the Big Bang was. We don't know what became before the Big Bang or whether that is even a reasonable question. But we do know that about 14 billion years ago, the universe as we know it today was created and started this expansion. We get our first glimpse 380,000 years after the Big Bang, and that's this picture. We're going to talk about this picture a lot tonight. This is what we call the cosmic microwave background. It is the afterglow of the Big Bang. It is a picture of the universe when the universe was about as hot as the surface of the sun, just a little cooler. And it was glowing then, just like the sun does, and that light has been traveling for nearly 14 billion years until it reaches us today. It is a glimpse back in time. Now, how do we start to think about this? Scientists go out, astronomers observe the universe, and then we put it together with our ideas, our theories. And the story tonight begins with Edwin Hubble. Edwin Hubble had access, shown here, to the 100-inch Hooker telescope that you can still see just outside of Pasadena in California. And he looked at galaxies. And he looked at galaxies, these are collections of stars, to measure their distances. So how do you measure distances in astronomy? Well, you can't just take a ruler and put it to the nearest star. Instead, we see how they appear. And so what Hubble did is he was able to look at stars and galaxies, and he could see how bright they were. The further the object, the fainter the star. Just like you see here, the further away a candle is, the fainter it appears. Now, he did this experiment alongside some work that was done by someone you probably have not heard, Vesto Melvin Slipher. And so what Slipher had done is he had gone and looked at these galaxies, and he had noticed that the light from each of these galaxies had been stretched redward. Now, if an object is moving away from you, its light waves will be stretched by that motion. And so it seemed that almost every galaxy in the sky, and this is work he did in 1917, was moving away from us. And that was a big mystery at the time. If they were moving towards us, their light would have been scrunched and made blue. So Slipher saw that all these galaxies were moving away from us by what we now call the redshift, how much the light is stretched. And he made a graph, a very famous graph in 1929, shown here. And so what you can see is that brighter stars, those are the nearby objects, compared to fainter stars, these are the distant objects, have a trend such that the nearby objects are only moving very slowly away from us, and the distant objects are moving much more quickly. The further, the farther. The faster, sorry. The further, the faster. So let's think what that means. Well, it turns out Hubble said this means that the universe is expanding. Now, I have just expanded the universe there for you. And let's overlay before and after and see what happens. If you expand the universe and see what it looks like to you, you can see that nearby objects move a little bit when you expand it. They're moving slowly. Distant objects, well, they move a lot faster. Indeed, you can see with your eye here, the further the object is, the faster it's moving away from us in this cartoon universe. Just what Hubble saw. And I want you to think about a universe that's expanding. It gets bigger, but let's think about what happens in the past. We look back in time, everything is closer and closer and closer until everything is on top of everything else sometime in the past. The Big Bang, the notion of everything being on top of everything else, sort of is a natural expectation of a universe that's expanding. Now, it turns out that if you go through and think of this as a scientist would, and we just do it as a graph, imagine a universe that's getting bigger over time. So right now, galaxies are some distance apart. In the past, they're closer and closer and closer. Imagine I can measure the steepness of that line, the slope of that line. Well, then it turns out I can extrapolate the universe back in time, and I can figure out how old the universe is. Hubble's law, that diagram I showed you of Hubble, that actually is measuring the expansion rate of the universe. It is literally measuring the steepness of that line. And so if you can measure, as Hubble did, distance versus velocity, you can extrapolate backwards in time and figure out how old the universe is. Now, when Hubble did that in 1929, he got that the universe was about 2 billion years old. And that was a problem because we already knew at the time the Earth was older than that. And so while we astronomers aren't too fussy, we do like our universe to be older than the things in it. That's a really important part of astronomy. And so it turned out they had measured the distance wrong, and measuring distances in astronomy is actually quite hard. It is very difficult to go out and measure things exactly right. And that remains a problem today, and a problem I'll tell you about at the very end of this talk that we are discussing at this conference. This is what I did for my PhD thesis. So here is a much younger me with my PhD supervisor, Robert Kirshner, and you can see my Hubble diagram there plotting out the universe. And the answer I got turned out to be roughly the same answer as the big project that used the Hubble Space Telescope to do this a few years later. And the age of the universe from the Hubble constant was that the universe was about 14 billion years old. This work continues today, and we keep on trying to refine it, but we're getting so accurate at it, we're beginning to see some problems where we're not sure if we understand exactly what's going on. Now, these are observations and cartoons, but it turns out we have a set of ideas. And these ideas go back to none other than Albert Einstein and his theory of gravity, known as general relativity. In 1907, Einstein had a revelation that acceleration and gravitation were indistinguishable, that the acceleration could be interchanged. Now, supposedly he had this thought when he saw someone fall off a building. And Einstein is the type of person that rather than thinking about going and getting an ambulance, he thought about, I think that person must feel weightlessness as they fall, presumably to some sort of demise. And I think that must always be true, that those things are interchangeable. That's a very subtle thought, but it turns out it took him 8.5 years to reconcile that thought with the physics of the day. And he created this new theory of gravity in the process, where you can literally, at the basis of it, not tell if you're in a rocket being accelerated or just sitting on Earth. Both have 9.8 meters per second squared of acceleration. But from that theory in 1915, Einstein predicted that space is curved by mass. And you could go out and predict things. And one of the things you could predict is how much the sun should bend space and therefore distort the background of stars that happen to be behind the sun. So in 1919, an experiment was done, led by Sir Arthur Eddington, and they went out and they looked at an eclipse. This is one of the images there. It was out of focus, it turns out. And they looked at the eclipse, they saw the stars behind the sun, and then they waited for the sun to depart, and they took another image. And they could see the stars had moved. And they had moved as predicted by Albert Einstein's new theory. And this is what made Albert Einstein famous around the world. He was already famous to physicists, but this made him an international celebrity. And the reason it did is because it was such a remarkable piece of intuition. You may all think that scientists like Albert Einstein have an idea that is completely unrelated to anything, and we go out and find it to be true. This is one of the only times in humanity's history where it happened that way. Normally, scientists are trying to figure out why something doesn't work, why a theory is not predicting what we see, and they come up with ideas. It is very, very rare for an idea to emerge from pure thought alone. But this theory is very powerful. It's never been shown to be wrong to this date in any way it has been applied. And it has predicted remarkable things that we keep discovering today, including very recently, for example, the presence of gravitational waves. Now, his theory of gravity allowed Einstein to do things that Isaac Newton could not do with his theory of gravity, Newton's theory of gravity. And one of those things was to go through and understand what would happen in a universe. When Newton tried to solve the universe, the only answer that made sense with his equations was that the universe was empty. That is, you can solve Newton's equations for a universe without end, which seemed to Newton to being the only way he could make the universe exist, and the only solution to that was that there was nothing in it. So this was something that bothered Newton, but Einstein could solve. But when Einstein did that, he got an answer he didn't like either. Not that the universe was empty, although he could solve that as well. But what he found is that the universe should be in motion. And he didn't understand how that could be. He looked around, nothing was moving. So he ended up putting a fudge factor in. And that fudge factor he called the cosmological constant, and we're going to talk about that later on. And it's energy that is fundamental to space itself. And it turns out through his equations, this stuff, if there is essentially mass or energy that's perfectly evenly spread through the universe and it doesn't change over time, it makes gravity push rather than pull. Now, it was shown later on in 1929, because he had this revelation in 1917, that, of course, the universe was expanding. And Einstein was later quoted on as being said he was acting like a donkey, holding on to this idea of the cosmological constant, because his equations naturally actually predicted what Hubble ended up seeing in 1929. So Einstein's theory allows us to put numbers to these cartoons. And it turns out if you're in an empty universe, indeed, the universe just gets bigger in a straight line over time. But it also tells you that gravity attracts the universe as it expands. So if the universe has stuff in it, the universe will slow down over time. And its trajectory will depend on how much stuff is in the universe. In the same way, if you go forward in time, you can predict the future as well. So a universe that's light, has nothing in it, just gets bigger and bigger and bigger. Whereas a universe that's heavy has so much stuff that it will stop expanding and actually go in reverse. And although all universes begin with a Big Bang, only the heavy universes end with a Gnab-Gib, the Big Bang backwards. So life in an Einstein's universe can be quite nuanced. You can, again, have an empty universe, but what happens if you have a light universe? Well, it slows down a little bit, but it keeps on getting bigger and bigger and bigger forever and ever. It goes on forever. There is a critical place between light and heavy where the universe comes to a halt in an infinite time in the future. That's the just right universe. A heavy universe has this trajectory where it gets bigger and then smaller. So it turns out these ideas are then related to curvature. Remember how I said that gravity actually bends space? Well, the whole universe gets bent by gravity. So a universe that has just that perfect amount of material, just right, is flat. It behaves just like you expect a universe should. It's kind of boring. But if a universe is heavy or light, then it turns out the space is warped. So a heavy universe bends onto itself. Gravity literally warps space onto itself, onto a giant sphere. A universe like this, if I head out this way, and I eventually had enough time, I would come back to where I am standing. It wraps literally onto itself in a way that is analogous to how the Earth seems to be flat here, but actually bends onto itself in that third dimension we don't think about right here. Well, the universe bends onto itself in a fourth dimension. And I find mathematics much more easy to understand that than my own brain, because I have no fourth dimension I can easily think of in my head. A light universe turns out to bend away from itself. Space naturally wants to bend away from itself in the shape of a saddle, or for you math students, the shape of a hyperbola. Okay? And so it turns out, if you think about it, a heavy universe in time has a beginning and an end. It's finite. And in space, it's also finite. It curves onto itself. It has a volume. A universe that is without end in time, goes on forever, also goes on forever in space. It goes on without end. Now, it turns out you can go out and you can test this. How do you test this? Well, before we talk about how we test this, I want us to reflect just on this image that was taken just a few weeks ago by the James Webb Space Telescope. You can, in this image, see literally tens of thousands of galaxies. There's a very bright star with the 6 points, and whenever you see an object with points, 6 points of light, those are typically stars. But when we look here, we are looking back in time. We are seeing objects. The nearest by objects are the ones most recently that have put their light out to us. When we go back further in time, then we're looking at those objects further past in the universe's past. We are looking at a very special part of space here. We're looking at a part of space where there is a giant galaxy and clusters of galaxies. Those galaxies are also warping space. They're bending space, making it like a giant lens. Now, a gravitational lens isn't quite like a lens you put in a telescope. It has more of the shape of the stem of a wine glass. So if you take a wine glass and break the top off, and you look at that, that's sort of what they look like. And I want you to look, it kind of makes things bend around in big spheres. And if we zoom in here, you can really see each one of those little streaks is a galaxy that is behind, very far away, and the light is coming through this giant lens and being distorted by the actual bending of space. Up at the top, you can see this very distorted galaxy, and that is a particularly interesting object because you can see it's right next to another galaxy. So that's almost like a bubble on your stem of your wine glass. It's a little imperfection in the lens that then distorts that image. People here are just getting their head around this image, but what we can see is the James Webb Space Telescope will allow us to look back in time to further than we've ever seen, with more precision than we've ever known, and we're just beginning to get our taste of discovery with this remarkable instrument. So we can look into the past. So I want you to imagine an experiment where we look at objects like Hubble, but we look so far in the past, so far away, that we're actually looking into the universe's distant past. That is the experiment that we can use to measure how the universe is changing over time, how the universe's expansion is changing over time. So imagine a universe that's empty. Then when I look into the past, the universe will be expanding at the same rate in the past as it is now. Whereas a universe that is heavy, well, then the universe will be slowing down, will be expanding faster in the past and slower in the present. If the universe is slowing down faster than that dotted yellow line, then I know the universe is heavy. I know the universe will end in a Gnab Gib, and it's finite. On the other hand, if the universe is slowing down on the other side of that line, so it's not slowing down very fast, then I know that gravity is going to lose, and the universe is going to expand forever, and the geometry of the universe is such that it is infinite, goes on without end. Now it turns out, in 1994, this is the experiment that I and many of my colleagues pitched to go out and get a bunch of telescope time and actually do this. And the reason we were able to do this in 1994 depended on many, many people's work in the decades before, and I'll just bring a couple of those to the forefront. The first is, if we're going to look into the distant past, we need something really bright. Hubble just used stars. Well, it turns out even with the James Webb Space Telescope, which we did not have in 1994, we couldn't see very far away the stars. But exploding stars, supernovae, now those were bright. These turn out are amazing explosions that outshine the entire galaxy of stars for about 20 days. They create most of the iron in the universe, and they're very rare. They only occur every couple hundred years in a galaxy. We think that they occur when 2 white dwarfs, so that is the remnant that will be at the center of the sun when the sun dies, are able to merge. Why do they merge? Well, it turns out that stars are sometimes born together as binaries, and they will do an elaborate dance in their life, and it turns out that gravitational radiation, this stuff that we can measure, and I'll talk about at the very end, actually takes energy away from rotating stars, and they eventually then merge together after billions of years. And when they merge, they create, and the theory exists for this, they create essentially a giant thermonuclear bomb. So very similar to the bombs that we have here on Earth, but much, much, much bigger. A bomb this bigger than the sun, more massive than the sun. And so they are remarkable explosions. And a team in Chile, known as the Calan-Tololo Survey, supernova search, led by a whole host of people, went through and did a big experiment to learn how to measure distances accurately with these objects. So that was a really key thing to have done. Another thing that had to be done is we had to learn how to use the new technology of digital cameras. Digital cameras are something that astronomy has had way before the public has had. And going out and using these digital cameras, which were 100 times more sensitive than photographic plates, which is what people used before, was a very challenging thing. And a group at Berkeley, led by Saul Perlmutter, had shown in 1994 that they could discover these distant exploding stars. Those things came together in 1994, and for us and our team, a team that I helped create, that was a really important thing that allowed us to go out and say, we can do this experiment to measure expansion back in time. For Saul Perlmutter's team, they had been working to do that experiment, and the supernova work of our team was really important to enable them, yet we needed their work on finding supernovae using digital plates. So the work was competitive, but we in the end really did rely on each other's expertise, and that's the way science should work, is there is competition, but there is an open sharing of information so that we can all go forth together. So it turns out finding one of these objects is looking for a needle in a haystack. This image is about an 8 megapixel image, but as I said, taken before most of the audience was born, at a time when computers were much less powerful than our phones are today, where a 1 gigabyte hard drive was the biggest hard drive available to anyone in the world. And we would take about 50 gigabytes of data in a night, and we would need to look for things that were these exploding stars on the other side of the planet, other side of the universe. And we did this by taking 2 images separated in time, and in this case you can see in the 24 days between these 2 images a supernova has come up. Now finding that with the primitive computational tools of the day was very hard, and interestingly enough we used machine learning AI technology in its very primitive stage, and we had to develop all sorts of tools that are now quite common but did not exist at the time. This object is about 5 billion light years in the past. So it exploded before the Earth was formed. That shows you the power. The problem, through all of that data, we would typically find 3 or 4 of these objects, and it required 6 nights on the biggest telescopes on the planet. So it was very challenging work, and it needed to have the support, because 6 nights of the community, because 6 nights of telescope time was a huge amount of telescope time for anyone back in those days. But persist we did, and after about 3 years, I remember Adam Rees, who I won the Nobel Prize with, sent me a preliminary diagram of our data, and it looked more or less like this. What we did is we plotted each exploding star, each supernova, gave us a distance and an expansion of the universe, and that allowed us to calculate what Hubble's did, the Hubble constant as we call it, or the expansion rate of the universe for that object. Each object has uncertainty, and that is why each object has a bar. And that tells you where you think 2 out of 3 times the correct answer lies within that bar. So in the nearby universe, you can tell you can't see what's going on. Are things below the line or above the line? You can't tell. On average, they're just on the line. But when we got to the distant objects, we could see clearly gravity was not going to win. The objects on the right are clearly, not a single one is consistent with gravity wins. But interestingly enough, every single one of them is above the universe slowing down, and en masse, with 99.9% assurity, they are actually above the line. And that is why we, in 1998, said it appears that the universe has gone and actually sped up over time. Now, it's not a very exciting diagram in the same way that Hubble's diagram wasn't that exciting. But interestingly enough, as I said, we were working in competition and collaboration, sort of, with the team of Saul Perlmutter at Berkeley. And at the same time, independent of us, they got the same answer with a different set of objects. And those things together made a sort of 99.995% assured answer. Not quite the standard that physicists like to say, this is a true discovery, and so we said it was evidence that the universe was speeding up. But more and more evidence over time has amounted, and it's for that that the 2 teams were awarded the Nobel Prize in 2011. And here we are celebrating. And I think it's really important to know that individuals receive Nobel Prizes, but they are actually the work of many, many people. And there are people on all continents except for South America on these 2 teams participated in this discovery. So why would the universe be speeding up? Well, Albert Einstein, as he always seems to do, had the answer. If the universe has a cosmological constant, that is, there is energy everywhere in the universe, spread thinly, then it turns out the universe can accelerate. The problem is it needs to be a whole bunch of the universe. 70% of the universe needs to be this stuff that we call now dark energy. Dark energy is the generic version of the cosmological constant. It turns out dark energy might change very slowly over time or not be quite the same everywhere in the universe at the same time. Only the cosmological constant is unchanging. So that was the obvious thing that we could look to in 1998 when this discovery was made. But it does allow us then to use the framework of general relativity and to test it really carefully, not just with our own method, but with all sorts of other methods. Now, here in Busan, we have a whole bunch of people have been using all sorts of techniques over the last 25 years to understand the expansion of the universe. And I'm not going to try to talk to you about each of those. There's a whole bunch of people working on this from all sorts and all directions. What I will say at this point in time, essentially all of the major experiments more or less are consistent with the picture that the universe is dominated by a cosmological constant. And I should say, Einstein's theory really does make an interesting prediction. And I put the Einstein prediction for what dark energy will work. And it's worthwhile thinking about this because it's a kind of confusing. Dark energy is part of space. It doesn't change over time. So as the universe, if we look back in time, the universe is smaller, right? But it's part of space itself. Its density, the amount of it per space, doesn't change. You and I, and the atoms we're made out of, we're in a smaller piece of space. So our density in the past is higher because we're all here and the universe is smaller around us. So it turns out that the expansion of the acceleration of the cosmos caused by dark energy is really strong now, but it will have been weaker in the past because the pulling on the universe by our gravity will have been more important in the past because our density was higher. So general relativity predicts that the universe will have a very funny trajectory where if we go back far enough, dark energy will be almost unimportant because the universe will be so dense with us and the dark energy will not have changed, it will essentially be irrelevant. So that means that the universe will be this funny curve where it slows down, and then about 6 billion years ago, it started to speed up. But what does it say about the future? It says that the universe will get faster and faster and faster over time. It will exponentially run away. So that is something we can go through and test. Not the future, but we can look to the past and see whether or not the universe really follows that funny curve. So the supernovae type 1a analysis, when you went and put all of the Einstein through it, basically said the universe is a mix of normal stuff like you and I, about 30%, and 70% had to be this dark energy pushing the universe apart. So as I said, there are many, many experiments that have looked at this, but I think the one that is just really quite remarkable is the one based on this image that I showed you at the beginning, the cosmic microwave background. And why is that? So when you look at that image, all those bumps and wiggles that you see in this image are real. They're not noise. They're actually little sound waves bouncing around the universe created right after the Big Bang. And it turns out the physics of sound waves, while complicated, is well understood. So we can go through and we can, it turns out, deduce what those sound waves look like and how they behave, and they tell us, for example, what the universe is made of at that time. Why? Because if I have a pond, let's say, of water and honey, and I throw a rock in a pond, the waves are different depending on what the pond is made out of. And the same is true of the universe. Now, the Big Bang was like throwing a bunch of rocks into the universe that splashed around, and then we get to look at the splash marks 380,000 years later. And so that gives us this amazing laboratory to see whether or not we can understand the universe. And it turns out the way we do this is by looking at how many sound waves there are of different size. So this is the actual data from the scientific paper, but I think it is the right thing to look at, even though it's complicated. So what we measure is how big the bumps are on the sky. Are they big bumps on the sky, or are they little ones? So we have big bumps here. We have little bumps here. And then the graph tells you essentially how many bumps there are of the different sizes. And you can see that the line here turns out to be the sound wave theory of what you might predict. And the data with very tiny little error bars tell you what you actually see in the universe. That is a very good fit for data to theory. It tells you we really know what's going on when you can have something fit that well. And it turns out that it tells us what's in the universe, and it points to something that we've had hints of for literally 100 years, something called dark matter. I'm going to talk about dark matter in just a second, but it's essentially invisible matter that has gravity but doesn't do much else. It turns out to make this graph work, you need to have roughly 25% of the universe be dark matter and 5% of the universe be atoms that we're made out of. So what's dark matter? Well, we're not sure. Lots of people are working on dark matter. They've been working on trying to figure out what dark matter is my entire career. We see everywhere we look in the universe more gravity than we see atoms. The only thing we can see in the universe are really atoms, all right? So we think, we hope, that there is some undiscovered particle. For example, like a neutrino, but different, that literally can travel right through itself, right through the Earth, right through the sun, but has gravity. Now, it's effectively invisible to us because the way we see things is when they interact with things, right? I can see you because light is coming and it's bouncing off you, coming to me. But dark matter is such that dark matter will go right through you. It doesn't bounce you, it goes right through the Earth, out the other side, does not stop. And you may think, well, that's crazy, but we already know neutrinos, an already discovered particle, do exactly the same thing. The difference is neutrinos occasionally interact, and we can measure them. So we're building giant detectors looking for dark matter, hoping that just occasionally they interact with the Earth, and we can see a signature of them. As of yet, giant vats of xenon put in underground mines where nothing else can disturb them have looked, but they have not yet found the signs of dark matter. But that ratio, 25% of the universe being dark matter, 5% being atoms, is very precisely measured by that sound wave. Now it turns out those sound waves, because it's pure physics, we know how big they are in meters. And the universe's curvature magnifies or demagnifies objects. So if a universe is flat, it more or less, the sound waves will have exactly the size you would expect for a flat universe where the lines are straight. But you can measure the curvature of the universe by how big those sound waves look. Much the way, if you think about it, if you have a curved spoon, it magnifies. If you have the other side of the spoon, it demagnifies. And the universe is the same way. So we can expect that if the universe has one of the three geometries, those bumps and wiggles will have a specific size, as shown in this diagram. And very accurately, you can tell that the universe has exactly the right amount of stuff to be flat. So 25% dark matter, 5% atoms, but we have this problem of missing stuff. All matter adds up to 100%, because the universe is flat. 25% is this dark matter stuff, 5% is atomic matter, then we have 70% mystery matter. The same mystery matter, it would seem, that the supernovae that I was involved with and many other groups have seen see. So we have a universe that is very messy. This is not a universe I would have ordered. 5% of the universe are the atoms that we can study here on Earth, that we know. 95% of the universe is stuff we cannot see or detect here on Earth. We can only infer it from astronomy. Now, you might rightly say, if I have to make up 95% of the universe with my theory, doesn't that just mean we don't know what we're doing? And that's a reasonable hypothesis. But science is about making predictions. And what has happened over the last 25 years is experiment after experiment has gone and tested this hypothesis, that the universe is only 5% atoms, 70% dark energy, and 25% dark matter, and it keeps giving time and time again the right answer, including, for example, that sound wave that I showed you, which has been essentially the prediction since 1998. So this leaves us the big questions. What is dark matter? What is dark energy? Many people are going through different ways to understand that. Dark matter, we can look at its effects out in astronomy. We can also try to hope that occasionally it interacts with things here on Earth. And that's how we're trying to understand dark matter. Dark energy is much harder. Dark energy is everywhere in equal amounts, but the amount on Earth is so small, like literally much, much, much less than a gram in the entire volume of the Earth. No one has really figured out a good way to look for dark energy other than astronomy. We're hoping maybe it will behave just a little differently than Albert Einstein's theory, but at this point, we haven't seen any evidence of that. I'm just going to get myself a drink of water here for a second. The good news is those are not the only two outstanding questions. There actually are other questions in this, what we would call cosmology area. Neutrinos turn out have mass. The model of particle physics says they shouldn't. We do not understand that. One of the other features of the model, the particle physics model that predicts the Higgs boson and all these things at CERN, is the matter and antimatter in the universe should have canceled each other out exactly. And it turns out that it canceled each other out almost exactly, but to about 1 part in a billion, it didn't. What is that? What's going on there? We don't know. So my hope is that the next Einstein will come along and try to understand these issues and come up with a theory that unifies gravity and the other forces of nature. And wouldn't it be great if we understood how gravity works within quantum mechanics, which we don't right now, and as a feature of that, suddenly questions about why neutrinos have mass, why the universe is not just full of photons emerged, and maybe the ideas behind dark matter and dark energy will also emerge. So we can go out and look, but we can also hope that someone will have that brilliant insight like Einstein had 100 years ago. Now, these are not all the questions that astronomers have. But one of the things that is not quite right is the measurement of the Hubble constant. That thing that I did for my PhD thesis and people have been doing, it turns out, for 100 years. If we do it in different ways, it turns out we get slightly different answers, and some people are beginning to wonder if what I think we would arguably say is the best method to use in the nearby universe, Cepheid variables, which are a variable star, essentially used by Hubble back in 1929, those and the measurement done by the cosmic microwave background. So the cosmic microwave background, it turns out when you fit those sound waves, one of the things you have to solve for is the Hubble constant, how fast the universe was expanding, back when the universe was 380,000 years old. Now, if you use general relativity and you take that measurement and you project it forward to now, you can compare it to the measurements we make now. And there's a discrepancy. The discrepancy is uncomfortable. It's not so big that we know there's a problem, yet it's not so small that we'd say there isn't a problem. So this is something that I think many people here are thinking about, and indeed there's been some major talks here that we're going to have to grapple with. This is the main thing that I would say isn't quite right in this messy universe that I've shown you. So stay tuned. Maybe there's a crack. Now, people often think, well, doesn't that make you sad? And I'm like, no, that makes me happy. Knowing everything about the universe is really boring. Knowing a lot about the universe, but being able to learn more, now that is exciting. So, and there are all these other questions. So people will have seen the James Webb Space Telescope. We have a radio telescope called the Square Kilometre Array that's slowly being put together. And I have a movie here of what a computer sees the universe coming together as gravity pulls things together and makes the galaxies and the stars that we see today. So we, with these new telescopes, are able to look back in time so far that we hope we're going to be able to see essentially the baby pictures of the universe and how the universe emerged from nothing into the rich universe we see today. And again, I'll come to this James Webb Space Telescope image. And one of the things when we look at this image, I didn't refer to, but I'll refer to now, is remember when we look further and further away, you're looking back in time, but you're also looking to when the universe has expanded more and more and more. So the light gets shifted redder and redder and redder and redder. Now, the James Webb Space Telescope is optimized to look in the infrared. So that's light that you can't see with your eyes. It's to the red of your eyes. And this is important because the really, really distant objects in this picture are so far shifted to the red by the expansion of the universe that you can't see them with conventional optical telescopes. You really need to look at it in the infrared. And so I'll just bring you to one of the interesting objects in this image. You can see the very red galaxy there. This was one of the first galaxies pointed out right after the release of this image. That object is very red. And so we think that object is probably more distant than any object that we have ever detected. Still needs to be confirmed. And since this, teams have looked through the literally thousands upon thousands of galaxies there, and they have found all sorts of objects, some of which they think are well older than this and even redder than this. So this is just the beginning of a new era of being able to look back into the essentially birth of the universe. The radio allows you to do this because it turns out the radio looks at things called hydrogen, just straight old hydrogen that's on its own. Now, as the universe created stars and galaxies, it turns out the hydrogen essentially gets disturbed. It gets what we would say ionized. That means the electron gets stripped, and it can no longer emit in the radio frequencies. And so with the Square Kilometre Array, we're hoping we're going to be able to look at how stars and galaxies essentially lit up the universe back in time. And these things are going to give us that picture into the universe's past. And the Square Kilometre Array is being hosted in South Africa and Australia, and we can expect it to come online slowly over the coming decade. But there's more. One of the biggest questions, to me probably as big a question as there is there life on planets beyond our own solar system? That is a question we're going to be able to start answering. We have these remarkable new giant telescopes being built here on Earth that complement the James Webb Space Telescope. And there are 3 planned right now. These telescopes will be coming online in the coming 5 to 10 years. And they will be able to look at those really early galaxies that James Webb Space Telescope looks at. But they're also, for example, going to be able to look through the atmospheres of planets as they pass through in front of their stars. So I want you to look at this image in the center. That turns out to be a real picture, not a Photoshop, but that is Venus passing in front of the sun. And you can see there's a rim of light. That is sunlight refracting, being bent through Venus's atmosphere. And when it does that, it will have imprinted on it the chemical composition of the atmosphere. And to get a sense of how this works, I have a picture, essentially a spectrum of the sun. And every one of those lines is a chemical signature of things in the sun's atmosphere. But as the light shines through the Earth's atmosphere, it picks up things. For example, up here in the corner, oxygen. So that oxygen is not in the Earth's atmosphere. It is a set of bands, very distinctive, that we pick up looking through the Earth's atmosphere. So with these giant telescopes looking at newly found planets, we have the opportunity to go through and see the signatures of whatever is in the atmospheres of planets. James Webb Space Telescope has already looked at a particularly, not something would ever have life on it, but we're going to be able to do this on literally all the nearby planets that go in front of their suns. So that is a very exciting thing to look forward to. Finally, we have black holes, and this has been a place remarkable work has done. Last night we had a lecture, which I'll refer to in just a second, about being able to look at black holes. But black holes are not just an idea. There are things we can literally look at, albeit not with optical light. So using these giant instruments spread across the United States and in Europe, we have been able to essentially measure the warping of space caused by gravitational waves. The way a gravitational wave works is it propagates through the universe, and it makes space sort of expand like an accordion, like this and this. And these instruments can measure the distance from here to an accuracy much, much smaller than an atom. And that has enabled us to do an experiment that Einstein, once again, predicted would happen, but he said no one will ever be able to make this measurement. It's too hard. Well, he didn't know about black holes coming together. He didn't know about neutron stars. But it turns out both neutron stars and black holes, when they merge together, they produce a very distinct pattern that we have now seen. And when we see them, we can actually know how big, for example, the black holes are. And there is a big map of all of these mergers of black holes together, and then a few neutron stars. And what we're seeing is there are all of these black holes that are huge, that are bigger than we ever knew existed. Why? How are they there? How is that working? We do not know yet. But we also know, and this was covered in the talk last night, that there are supermassive black holes that are literally millions to billions of times bigger than our sun. And using this radio sub-millimeter, so it's not quite the normal radio, it's a little higher frequency, spread across the whole of the Earth, we have been able to, we collectively as the community, have been able to literally image a black hole in the center of a nearby galaxy and at the center of our own galaxy. And the theory, again, Einstein's theory of general relativity plus complicated physics of stuff trying to fall onto a black hole, essentially has created what we expected to see. And these are truly amazing images that allow us to essentially see the shadow of a black hole. So people often ask me, why do we do this? These are great. This is so cool. But understanding the universe is wonderful, and we need to keep doing it because it's part of what brings humanity together. These experiments you're seeing are across all sorts of societies, all sorts of nations. But it turns out it's also very useful. If you look at your phone, the camera, CMOS technology, created on a mission to Jupiter. The World Wide Web, created as part of CERN. Wi-Fi, created by Australian astronomers trying to look for evaporating black holes. The touch screen, again out of CERN. The GPS, based on the space program coupled to general relativity. Those are things that you would not have just invented by a program because they're beyond our thought. You get these amazing inventions by thinking about the universe. So it's worthwhile loving the universe, but also know it turns out to be useful as well. And so, what is our future in all of this? Well, I'm here to tell you that you think global warming's bad now. Wait 1 billion years. The sun's nuclear reactor is getting hotter and hotter. 1 billion years is a very long time. And 4 or 5 billion years, the sun will get so big, it will eventually, if it does not envelop the Earth, it will be very close to enveloping the Earth. So the Earth has, at most, about 5 billion years left into it. But it will, unfortunately, become uninhabitable over the next 1 billion years, independent of what we're doing, although geoengineering and stuff is possible. But I do want you to think how long 1 billion years is before you get scared and have nightmares about it. It's a long time in the future. But the future of the universe, that's dark energy. Why? Because as I told you, as space expands, dark energy is part of the space. So the more space there is, the more dark energy is, and the more the dark energy can push on the universe. And so the universe runs away, meaning that us, who are not being created with space, get drowned out. The universe expands faster and faster, such that eventually space is expanding faster than light can travel through it. Turns out this is already happening in our universe. If we look at an object, for example, in that James Webb Space Telescope, one of the faint galaxies, the light that's emitted today will never reach us because as the photon tries to travel through space, Space is being created, and the space gets created faster than the light can travel through it. That is the fate of our universe, because eventually every part of the universe that is expanding away from us right now will eventually be too far away to see. So unless something dramatically changes with the universe, we expect, unless dark energy suddenly disappears, the universe will, at an ever-increasing rate, expand and fade away, leaving cosmologists like myself and the astronomers here at the IAU unemployed. So let's act now. Thank you very much.
Thank you. 네, 좋은 강의.
Thank you very much, Professor Schmidt. You have already given him a big round of applause, but please, once again, give a big round of applause to Professor Schmidt for his wonderful lecture.
네, 감사합니다.
Thank you very much. Even before I listened to this lecture, I have wanted to introduce that in Korean. I have explained it as an appearance of the universe. And now after listening to the lecture, Professor Schmidt has really talked about the state of the universe, or the dynamic state of the universe. The universe is not stagnant, it is changing as we speak, and the universe is expanding as we speak. Hubble has discovered that, and Professor Schmidt and many other astronomers around the world are now discovering that the universe expanding at an accelerated rate, faster and faster, based on observation of supernovas. That is really amazing. By observing multiple supernovas, the researchers have talked about ways to observe bright objects, and also by measuring the distance of objects in the universe, they can do that in a universal scale, and then they can trace back in our time and see how the universe has changed over time. And Professor Schmidt, supernova observation looks really challenging. It requires a lot of people's efforts and the sweat and tears of many graduate school students and a lot of computational research. And Professor Schmidt has briefly talked about how difficult it is to do that. Now we are going to have a Q&A session with Professor Schmidt. On both sides of the room, we have a microphone. So if you have a question, please come forward to the microphone. And yesterday we have done the same thing, and especially young students were so passionate. And there was one very young student who wanted to ask a question, but he was so short, so we could not see him from here. But if there is any children who would like to ask a question first, we would let you go first. So if you raise your hand, if you're in the elementary school or even younger, please raise your hand now.
네, 좀 수줍은 것 같습니다. 그럼
Okay, we don't seem to have any elementary school students, so we will proceed as announced.
저기 지금
Yes, if you think you seem to be the youngest person in the line,
마이크 앞으로 가.
So please come to the microphone. Could somebody adjust the height of the microphone? Or can you take out the microphone? Professor Schmidt, you talked about space equation, but I could not understand that. I tried to listen to your lecture as much as I can, so did not understand everything you said. Can you explain what's the space equation one more time?
All right. General relativity is something that you normally do for a year in graduate school, but we will try to get to it tonight in a few minutes. So it turns out the equation for space from Albert Einstein essentially tells you that how dense the universe is. So density is how much stuff there is in a piece of space. And general relativity then tells you, if you know that, it'll tell you how the universe gets bigger over time. So that's really what the essence of that space equation is. But you'll need to keep studying, and when you get into graduate school, my friends here would love to teach you general relativity, and you can get all of the bells and whistles on it.
네, 감사합니다. 네, 도움이 되셨길.
Well, I hope it answers. Each objects, they pull together because of the gravity, and there are many different things in the space, and you can see whether the space is expanding or contracting or accelerating. You will be able to learn, study hard, and then you'll be able to learn, and you can understand that based on space equations. But to understand that, you have to study more. So next question will go. Well, there could be some confusion. So from my positions, we'll start with the right side. So we'll go to the left side. The first person standing on the left microphone, please ask a question, and then next time I'll ask the person on the right side of microphone. So please go ahead.
Middle school student in Korea, and your lecture was very impressive. What do you think is beyond the universe? I would like to hear the personal opinion of you.
Yeah, so people always want to know what's beyond the universe. So the first thing we have to contemplate is what I have shown you tonight, is that the observations made by many of the people in this room show that to our best estimate, the universe goes on forever. It is infinite. So I want you to think already, what is beyond infinity? That is a very tough concept to come to grips with. We can only see a part of the universe that is finite because the universe is only 13.8 billion years old. So we can only see the area of space where light could travel over 13.8 billion years. But it is possible, it turns out, that well beyond that, the universe might actually be finite. We just can't tell it. It might be that our little part of the universe at the time of the Big Bang may have been infinite even back at that time. There might be other universes beyond essentially our 4 dimensions into higher dimensions. We don't know. So there are many, many people who speculate, and they even use theory. But the question, I say, is what can I measure to test these ideas? And it turns out it's really hard to create ways to test people's ideas about other universes or what's beyond. So at some point you have to ask yourself, is this physics or is it metaphysics? Are we thinking about what is actually testable? Now, we don't know. So I encourage my theorists to keep thinking, but they always need to have that idea of how we test this, because anyone can come up with ideas. Some of them will be crazy, but it's only by testing them that you know if things that look crazy are actually real. And so that's the really important part about it. So I literally don't know.
Thank you.
네, 감사합니다.
Thank you, Professor Schmidt.
그럼 이제 반대쪽
Yes, on the other side of the room.
Thank you for your great achievement and lecture. I want to ask you about our current state of our understanding of the universe. I acknowledge that this is a common asked question, but I still wanted to know your opinion. Given all these massive innovations like the heliocentric model of our solar system and theories like Newton's mechanics, constantly refined with quantum mechanics, how much do you think our current models are correctly depicting the truth?
So this comes down again to what I would describe as a philosophy of science question. So clearly the universe behaves in a certain way. It's not random, and although quantum mechanics means that individual events end up having a probability, they still behave in essentially a predictable manner as a whole. So physics is all about prediction, and as long as we're predicting everything we see, that is sort of what reality is to us as humans. But we can normally always pick apart our theories, and there are assumptions. For Newton, what is mass? Well, you got to get back to the really foundational theories. If you want to go into, for example, string theory, which is an attempt to unify gravity and quantum mechanics, there are still underpinnings of quantum mechanics, and asking why do those exist? So you can usually always take an idea and ask a question more fundamental than what the theory has. And so there is that aspect. The other aspect is our information is finite. So when we're testing theories, you imagine we suddenly discovered the theory of everything. How would we know that we had discovered the theory of everything? We would be testing it. We'd keep on getting the same answer. There'd be some mistakes of observers making mistakes. We wouldn't be sure. We'd eventually keep working, but we'd get bored at some point. And we'd work on something else, like biology or the weather that's really hard, that is more interesting at the time. So it's not clear to me that we will ever know for sure that we understand everything. But when we are able to predict things with a high degree of accuracy, that means we do understand things pretty well, but it doesn't tell us that we understand things perfectly. And general relativity, Newton's laws were essentially thought to be perfect in 1900, no reason to doubt them. Suddenly Einstein comes in and shows actually they're an approximation to a better theory. That may well continue into the future. You don't ever really know. So I think the answer is probably we'll never know things perfectly, but we will be able to predict more and more accurately. And in the end, it's probably us getting bored and wanting to do something else that limits us more than anything. Or should I say running out of money. It turns out it's expensive to do some of these things.
Thank you. I tried to figure out something. Really, thank you.
Thank you.
네. 네, 감사합니다. 또 이제 반대
So going to the next question. Hello. Using AI, observing watching the space, and I also would like to resolve the global challenges like climate crisis. I'm a high school student, 9th grade student. Upon listening to your presentation, you talk about digital camera and using machine learning. You try to analyze and process the image. You talk about that. But you did it a couple of years ago, and you successfully did it using machine learning and sort of AI. But now, 2022, AI has achieved a dramatic development. Now, what kind of method do you use to process, to analyze the images? And also, other astronomers or astrophysicists, what kind of program do they use? Are they using AI or machine learning? What kind of technique are they using?
So that's a good question, and it's changing quite a lot. So we use, as physicists, typically statistical methods that allow us to check our theories, our physical theories. But sometimes tools like AI are useful where we want to solve problems that humans would normally be trying to do. So AI is really good at discovering patterns in data that is embedded in very complex data sets. It doesn't tell you what physics is, but it can see patterns that then you can use to think about what is the underlying physical theory. In my case, I used AI to try to find the exploding stars rather than going through each galaxy eye by eye. It went through and took a lot of the load off the humans that were trying to figure out, is that just a mistake in the image or is it real? So that's how we used AI back 25 years ago. It was very simple AI, nothing like we have now. So we continue to use mainly statistical analyses of the equations of physics, but we use AI as a tool to do some of those analyses that are just really difficult to use with conventional statistical tools. Okay, so one of the problems with AI is it kind of gives you answers, but it doesn't really tell you how it's thinking. And so it is rather difficult sometimes to use as a way of understanding physics, but rather it's a tool to do physics and to take some shortcuts and, as I said, to find patterns that are really difficult to see other ways. So it's a real mix. But we're learning how to use AI just like the entire rest of the world. And if you think most of AI right now is used to give each of you on your phone what you want, that's a very different problem to solve than to try to figure out how the universe works. So we still have a lot to learn, I think, about how to use machine learning and artificial intelligence in astronomy, but there are a lot of people here who are using it in various ways. Yeah.
네.
Thank you.
감사합니다.
네, 감사합니다.
Thanks a lot.
네, 조금 전에 학생 질문
Regarding this question, in the 31st General Assembly of IAG, we had a had session about how the field of astronomy can utilize AI better. And we are running out of time. So I believe the two people who are standing closest to the microphone will be the only ones who will get to ask questions now. So this side of the room.
It is an honor to be able to ask questions directly to my favorite professor. For what I know, you've identified the expansion of the universe through looking at type 1a. I'm curious about the reason why you choose to use 1a for your research.
Okay, thank you. So in 1994, when we started this project, we used type 1a supernovae because they were so bright. They were one of the only things we could use to look to the vast distances needed that you could measure distances with accurately. So we chose them out of convenience. There were no other stars bright enough to see, and it turns out when you try to measure distances with galaxies, the galaxies age over time, and so when you look back in the past, they're very different than they are in the present. Now we have to worry about the supernovae may be different over time as well, but we expect those changes to be a lot less, and they have been shown to be a lot less than the changes to galaxies. So it was out of convenience, because remember, astronomy is an area of physics, but it's different than physics in that we don't get to create our laboratory experiments here on Earth and change them. We literally go out and look in the universe for experiments that can be done just by looking at the universe. So you kind of have to go out and find your laboratory in the universe to be an astronomer, rather than make your universe like most physicists do in the lab here on Earth. Thank you.
네, 감사합니다. 네, 그러면 마지막
So this will be the last question. Regrettably and unfortunately, this will be the last question. So going to the next question, please go ahead. Hello, everyone. Today, first of all, thank you so much, Professor, for your passionate and very interesting lecture. I'm a high school student. Oh, sorry. I am a teacher teaching earth science at the high school. I watched all of your lecture via online, and whenever you teach your students, I was able to learn a lot from you. I want to take this opportunity to express my gratitude. Here comes my question. I have two questions. First question. Professor, you talk and you did a lot of research about the expansions of the space, and you have a hypothesis that space has been contracted or space has been expanded. Which one did you choose as your hypothesis? Or second, in order to verify your theory that space was expanding, did you focus your research? Or did you happen to just find out that the space was expanding? And now, second question, dark energy is extremely important. And I've been doing a lot of research based on the importance of the dark energy. And I read an article that a certain experiment was done. So in an empty space, there's no oxygen or nothing at all. And they put the metal bar, and then the metal bar began to depart each other. There was a space between these two. So within this empty space, there is a so-called undetected energy. What kind of relation does it have with the dark energy?
Thank you. So the first question about what was the hypothesis that we tested back in 1994. So we were testing the general relativity model of the universe, and we were pretty sure general relativity was right, but we were testing general relativity. And back to our first question of our young girl there who asked, you know, the equations of general relativity had, at the time, we assumed one parameter. And that parameter was the density of the universe. And we assumed the universe was just made out of the stuff in this room, plus dark matter, stuff that worked just with normal gravity. So that was essentially the test, general relativity, and then the density of the universe. That was what we're trying to test. And you got a family of outcomes, and which one would be correct? Well, none of them were correct. It turns out you needed another parameter, which is how much cosmological constant there was in the universe to fit the data. There was no way to fit it with just the normal matter like you and I are made out of. So that is what we tested and how we went about it. With respect to what you've described, which is, I believe, the Casimir effect, where you can go through and you can essentially test if the creation, essentially, of particles that happen in quantum mechanics due to the Heisenberg uncertainty effect and more complicated ways of thinking about it, whether or not that prediction exists. And the answer is it does. It is sort of as you would expect. Then the question is, why does that dark energy, which is sort of there, and if you calculated how much dark energy there would be in the universe, it would be literally 50 orders of magnitude more than what we see. And the universe would have started accelerating into oblivion right after it was born. There would be no galaxies, there would be no stars. So that was actually identified as a question back before 1994 when we made this. That was particularly brought by a physicist who's just passed away, Steven Weinberg, certainly one of the great physicists of my lifetime. And so that remains a question, is why do the creation of particles as proposed by, that occurs via quantum mechanics, why do they not act as dark energy? Because they clearly don't, we wouldn't be here. So it's always been assumed that that dark energy would somehow cancel out to zero, and maybe it does, but it's just really hard to understand why it would cancel out with a decimal point and 50 zeros and a 1, rather than just 0. So it remains a very open question of why is the universe here in its current state at all? Why hasn't quantum mechanics created dark energy way bigger than what we measure, such that we couldn't exist? So still more to learn.
네, 감사합니다.
감사합니다.
So was it a surprise when the data, the theories didn't really fit the data?
Yeah, so it was not just a surprise. When Adam Rees sent the first glimpse of it, and I was analyzing it, I just assumed something. Oh my God, Adam, what have you done wrong? And so we spent the time working very hard trying to show that it was wrong, and then we had to go to the whole team and say, guys, we need to all have a look at this. We're all going to work through it. And after a period of several months, there was just no way to make it go away. And people think you're going, eureka. You're kind of going, wow, this is interesting. And you're also thinking, there's no way this can be right, but it seems to be. And you're asking whether or not, when it's shown to be wrong, whether or not you're going to have a job in astronomy or just be a laughingstock. So it's quite it was something that made us very, very nervous at the time. Yeah.
Right. Thank you so much. 네, 그래서 데이터를 교과서
Trying to fit the data into the theories in textbook, we get nervous, but I think we need to be brave and be confident that we have done the best job of analyzing the data based on the trust with the team members. And the person, Professor Schmidt, was the person who was brave enough to ask the question. Of course, we were joined by many participants online. Of course, there are so many people who wanted to ask questions, but because the time is up, we have to wrap up now. Once again, please give Professor Schmidt and ourselves a big round of applause.
네. 야. 네, 어제와 오늘에 걸쳐서
So following yesterday, in celebration of the General Assembly of IAU, we've had public lectures, and I think we've had a great time. We had a ball on these lovely summer nights, dealing with these wonderful concepts of black hole and expansion of the universe. As Professor Schmidt has said, international collaboration is important, but it is also important for the general public, laymen in our society, to have the basic understanding and curiosity about the basics of and the fundamentals of the universe. I look forward to your stronger interest and the students. So with your hard work, it would be nice if you could all understand this equation of the universe. I am Kim Jung-ni. A safe trip home. Thank you very much.
Thank you very much.
Gonna do the picture?
Yes. All right.
브라이언 교수님과 기념 촬영이 있으니까
There will be a photo session with Professor Schmidt, so please come for a group photo session. And those of you who can